All right, welcome back, everyone. So we're very fortunate to have Peter Shor and Ken Brown on our team, and they're both going to talk about some of the most interesting algorithms for us in the near term, QAOA and quantum chemistry algorithms. So first, Peter Shor.
Okay. So I'll be talking about the QAOA algorithm. And first, let's see this. Why is this not
Just set it into presentation mode.
there? Okay. There, that's better. So what am I going to say? First, why are we looking at this algorithm? Second, what is it? And third, future work. And at some point along in time, I'll say something about the disadvantages of it. And, the hopes. We really don't know that much about the QAOA yet. And maybe one of the advantages of small computers will be to tell whether it really works or not. So, applications. So, as you probably all know, the reason people are so interested in quantum computers is that theoretically they can solve some problems much faster than classical computers. So which problems? Well, traditionally the answer is, there's Shor's algorithm for factoring, there's Grover's algorithm for search, there's physics and chemistry simulations, which I guess Feynman was the first person to propose probably. And why aren't we worrying about these? Well, you can look at the resources for factoring on a quantum computer. So without error correction, the algorithm needs maybe 5,000 qubits to factor cryptologically significant numbers. But it needs hundreds of millions of gates to do that. And if you want to run hundreds of millions of gates on a quantum computer, you need fidelity for each gate of order 10 to the minus 8th. And that's pretty much impossible experimentally. So there's a theorem about error correction that says as soon as you get your gates error below a certain threshold, which is 10 to the minus 5th maybe, you can use quantum fault tolerance and run arbitrarily long programs. The problem with that is the overhead for fault tolerance. Instead of 5,000 qubits, maybe you need, close to 1 million qubits to run the algorithm fault tolerantly. And since we have 70 qubits nowadays in quantum computers, we're not going to get there very soon. So what we'd really like are near-term quantum algorithms, and particularly the people who are designing and building quantum computers would love to see near-term quantum algorithms that run on small quantum computers, solve useful problems, don't need enormous numbers of qubits, and they don't need extensive error correction. And this is why people are looking at the QAOA. It's low depth. That means it shouldn't need too much coherence. And there are some results that indicate it's fairly robust to errors. Just being low depth is already a very good indication that it's robust to errors, but it seems even more robust than just the low depth would indicate. So how many qubits does it need? Well, essentially, it needs enough qubits to store the problem. So this makes it infeasible for, largish problems, but you probably can't really do much better. So this is why people got so excited about the QAOA when Eddie Fari, Sam Gutman, and Jeffrey Goldstone proposed it, because it was, I guess a theoretical computer science algorithm that looked like it might work on small quantum computers. So what is it? Well, first let's go back and talk a little bit more about quantum computing. The Pauli matrices are sigma x, sigma y, and sigma z, and we'll only need sigma x and sigma z. So what sigma x does is essentially it's a NOT gate. If you input a 0, you get out a 1. If you input a 1, you get out a 0. If you put a superposition of 0 plus 1, that's one of its eigenvalues, so it comes out superposition of 0 plus 1. And sigma z is the gate that applies a -1 phase to a qubit which has value 1 and a 1 phase to a qubit that has value 0. And there's one thing very confusing about these gates is that they're both unitary matrices and Hermitian matrices. And quantum gates are unitary Hermitian, or are represented by unitary matrices. Quantum measurements are represented by Hermitian matrices. So these matrices can represent either a gate or a measurement, and they behave, sigma x, being used as a measurement is quite different from sigma x being used as a gate. So you have to be careful and not confuse those. And of course, the quantum computing literature doesn't really distinguish except from context. It doesn't say this sigma x is the gate, this other sigma x is a measurement. You just have to look at the paper and read it and understand it, and remember that there are two different things, so don't get confused. And we're going to be using sigma x and sigma z for both gates and measurements later in the talk, so don't get confused. So now let's go back and let me tell you about a little piece of history where theoretical computer scientists kept on saying something and nobody paid any attention to them. So this is about adaptable algorithms. So what industry needs is it needs optimization algorithms that work well and that don't require too much time spent by expert researchers to adapt them to specific problems. Because, if you need to hire, a top theoretical computer scientist to solve your optimization problem, and you have 100 optimization problems you need to solve, and there's only maybe, a few hundred top theoretical computer scientists in the world, and there's all these other companies that have these other optimization problems that want to solve, you're never going to get them, considered by top theoretical computer scientists. So, the classical examples of adaptable algorithms are genetic algorithms and simulated annealing. And when these came out, theoretical computer scientists basically sneered at them by saying, well, look, Kirkpatrick uses simulated annealing for the traveling salesman problem, but we can solve the traveling salesman problem much better than Kirkpatrick. And, you apply simulated annealing to any other problem. If theoretical computer scientists sit down and get to work on this problem and seriously consider it, they can probably come up with better algorithms. But there's way more problems, optimization problems in industry than there are theoretical computer scientists who come up with clever algorithms for each single one, so you need something that works for a big class of them. And this is one of the hopes that the QAOA will work for. And in fact, deep learning came up in the 2000s, and even theoretical computer scientists don't seem to be able to do better than deep learning. So deep learning really works, and we don't understand why. So what is the QAOA? So we're going to explain it by giving the example of max cut, which was the major example in the original paper. So what is max cut? So suppose we have a graph. So this has vertices and edges, and the edges connect pairs of vertices. And what we would like to do is we'd like to divide the graph into two parts so as to maximize the number of edges between the two halves. Okay, and here is one of the answers. There are only three edges between blue vertices or red vertices, and 8 edges between a blue vertex and a red vertex. So the blue vertices form one half, the red vertices form the other half, and the cut is 8 edges. And that's the best you can do for this graph. So that's max cut. So how do we apply the QAOA to it? Well, what we're going to do is we're going to assign one qubit to each vertex of the problem. And what we'd really like is for adjacent qubits to be in different halves of the partition. So recall this, Pauli matrix, sigma z, which is 1, 0, 0, minus 1. It gives a phase of 1 to a qubit, which is in the 0 state, and a phase of minus 1 to a qubit that's in the 1 state. So what we're going to do is we're going to measure we have a qubit for each thing. When we measure the state of our quantum computer in the sigma z basis, it says some vertices get a 1. Some vertices get a 1 and some vertices get a 0. And that means that we put the 1s in one part and the 0 in the other part. So to maximize the number of edges in different halves, we want to make the sigma z sub j, sigma z k, minus 1 for as many different edges jk as possible. So this is, just the optimization problem with, we've assigned a qubit to each vertex and restated it that way. So we want to maximize C of jk, where C of jk is this operator. Okay, so the idea of QOA is somehow we're going to start with a graph in an equal position of all possible partitions. And that means putting each vertex in a superposition of a 0 and 1. And then we are going to apply a sequence of unitary operators to the set of qubits and measure the resulting state in the z basis. So what is the expected value of the cut? Well, it's just the expected value of the operator sum Cij over all different vertices, over all different edges, I should say. So we want to maximize this. And how do we maximize this? Well, what we're going to do is we're going to apply an alternating sequence of operations to our state psi. So we're going to alternate applying the unitary C gamma 1, beta B, beta 1, C gamma 2, B, beta 2, C gamma 3, B, beta 3, etc. And beta j and gamma j are really angles that tell us how long to apply these operators if you thought of them as Hamiltonians. So basically we're going to rotate each, the state around, around C and then around B alternately. And we're going to use some sequence of angles, and we're going to try to optimize this sequence of angles to yield the best results. So why should this work? Well, the idea is if you use a product of P operators, then, or I guess this is really two P operators, then the expected value for jk only depends on the structure of the graph within P edges of the edge ij. And so there aren't too many graphs like this. Okay, so here, if the idea, so here is an edge, and if you want to know the expected value of the cut across this edge, so I guess that's a probability that these two vertices are in opposite halves of the partition, then to figure this expected value out, you only need to look at the subgraph of radius.
You can use the handheld if you want.
Oh, you only need to look at the subgraph of radius
You gotta
2.
turn it on, I'm sorry.
Oh, okay, that would help. Let's see. There we go. We have to look at the subgraph of radius 2 around this edge, and the expected value of that, of the of the contribution of that edge to that cut just depends on this graph within radius 2 of this edge. So what we need to do is we need to maximize the value of this thing for all edges. Okay, so I should go back and talk more about these operators. So B is actually a sum of operators for each vertex, and C is a sum of operators for each edge. And for the QA-OA to work, all of the B's need to commute, and all of the C's need to commute. And since the C's are sigma Z, you can easily check that sigma Z across one edge commutes with sigma Z for another edge, and similarly the operators B just depend on the vertex, and the vertex operator on one vertex just automatically commutes with an operator on a different vertex. But the B and the C's don't commute, and you need that because if they all commuted, then this would be a classical algorithm, and we couldn't do better on a quantum computer. And so for the QA-OA in general, you need the B's to commute, the C's to commute, and you want them not to commute with each other. And for the max cut, this is the B's and C's that Ed Fari chose, or Ed Fari et al. And now what they did was they took P equals 1, and if you think about graphs of degree 3 with P equals 1, there are only 3 different possible kinds of subgraphs to consider, and optimizing them so you find the optimal value of, I guess, beta 1 and gamma 1 that gives you a good ratio for all 3 of these subgraphs. That gives you a ratio of 0.6924, which is better than the naive algorithm of choosing a random partition, which gives you an approximation ratio of 2/3. So that was, well, I mean, that's some hint that the QA-OA might be good in general. So what do we need this to do better? Well, what we need to do better is to find this optimal sequence of operators. And for P equals 1, it was basically found by hand, and this is not really going to work very well for large P because the equations are impossible. So you have to find some good way of figuring out this sequence. And then you have to see whether this works well for max cut in general or other optimization algorithms in general. So you can ask, will gradient descent work? Why would we think of gradient descent? Well, it's a magic ingredient in machine learning. So maybe the magic ingredient in this as well. So we don't know. So some people are studying it, including some of Aram Harrow's students at MIT, and the preliminary results are in, and they don't really tell us the answer to the question yet. And it's not clear that we can really learn the answer in the question until we get a quantum computer. What we also would really like is there a quantum algorithm for solving this gradient descent, or do we have to do it on classical computers? Well, that's another good question. And there is a quantum algorithm for gradient that works better than classical algorithms in some sense. And this was discovered by Steve Jordan when he was a grad student of ours at MIT quite a while ago. But can we apply this to get a gradient descent algorithm for QA-OA? We don't know that either, really. So what can we do? Well, one challenge is find a problem where QAOA works better than the best known classical algorithm. And we actually had this for a few months, but then a whole bunch of very good theoretical computer scientists got together and showed how to do just as well as our QAOA algorithm classically. So, well, this gives us hope that QAOA, even if it's not better in general than the best classical algorithms, might be one of these heuristics which works well without actually having to go through all sorts of analysis to figure out what the best classical algorithm is. So it might be one of these, I guess, adaptable heuristics. And, I think one of the great things about small quantum computers is that it can, we can use them to discover whether QAOA really works in practice. And another thing is that QAOA works for so there's a recipe for optimization algorithms that have purely local constraints for how to get QAOA, but lots of optimization problems also have global constraints on them, and there's no immediate way that we see to deal with global constraints for QAOA. So, of course, on the other hand, theoretical computer scientists have shown that you can turn any optimization problem with global constraints into one with purely local constraints with polynomial increase in overhead. But then this is polynomial increase in overhead, which is not really feasible in practice. Okay. So this is my last slide. I want to say that one thing, if QAOA really works, one thing that we should consider is designing programming languages and compilers and everything just for the QAOA problem and not for general quantum algorithms, because one expects that if they were designed specifically for QAOA, they would be more efficient for that problem than general compilers. And in fact, I think this is something that we should consider for all special classes of quantum algorithms, because right now quantum computers are so small that we may not be able to afford general compilers, general programming languages, general everything else in architecture as well. Okay, thank you.
Are there any questions?
Yeah.
I'll speak loudly.
Okay. Oh, you can have a.
What are your thoughts when, people already have 50 to 70 qubit? As we get into a few hundred qubits, what are the kind of applications we're likely to see? So one possible example is what you mentioned. What are the other classes of applications that we are likely to see?
Well, I think Ken will be talking about quantum chemistry, which I think is a very promising application, and simulations of quantum physics, and maybe we can figure out why high-temperature superconductors really work, which is something I don't think physicists know yet. And the other question is, are there any theoretical computer science type algorithms that would be useful? And QAOA looks, the reason people have been spending so much time looking at QAOA is it's the most promising of all the ones that we have looked at, and it's not even that promising. I shouldn't say it's not even that promising. We don't really know we don't really have any idea about whether it will work well for general problems or not. So, and it's the, the best of all the ideas we've had. So there really are not that many good ideas for optimization and anything outside of simulating physics and chemistry for small quantum computers. On the other hand, once actual real computers got built, people discovered all sorts of algorithms by playing with them that they would never have been able to discover by theory. So this is something which hopefully real quantum computers will make happen.
Thanks.
I have one question from theoretical computer science perspective. So, I mean, what are your, if you want to bet, when could we decide about the status of BQP? Like, where would we fit? Obviously, it's so there was this recent result with a Oracle separation that it's more powerful than PH. It was able to solve. There was very recent result. So yeah. So when do you think it's just a general guideline of when do you think it could happen, when we can fix this BQP forever in that complexity classes?
Well, so if we cannot separate NP from P space, we're not going to be able to fix BQP in the complexity classes. So, and I don't think there's much hope of seeing a proof that NP is not equal to P space in the next decade or two. So it may be that we can actually, maybe that we'll be able to factor numbers on quantum computers before we can prove that they're more powerful than classical computers. So, those events are both, I think, very far away in the future.
Hope not to put you on the spot, but I'm curious about the history of how you came up with Shor's algorithm and just like how did it come to you? Yeah.
So this is going to, I'll try to be short. So I was interested in physics as an undergrad and took a lot of physics courses, including quantum mechanics. And then I saw Charlie Bennett give a talk about quantum key distribution and started looking at quantum computing papers. And then Umesh Vazirani came and talked about Bernstein and Vazirani, which you just saw. And then I was on a program committee and I saw Dan Simon's paper. And that really gave me the idea. So Dan Simon's paper solves Simon's problem more quickly on a quantum computer than a classical computer. But Simon's problem is not something you would actually ever want to solve in practice, but it gave me the idea for periodicity. And once I had periodicity, I discovered the quantum Fourier transform and how to apply it to solving discrete log and factoring. And unfortunately, we rejected Simon's paper from the conference. And so I was outvoted. And in retrospect, I really should have been jumping up and down and yelling and saying, you have to take this paper. But I didn't. So it got into the next conference along with my paper. Yeah.
You mentioned that one of the challenge of QLA is to find the control parameters alpha and beta or the operators. So do you think like classical quantum hybrid algorithms like VQE will be a good candidate to find the control parameters?
I think it's very possible, but I don't know.
Okay.